Welcome to the NHP webinar program. Today we'll be following on from our earlier presentations on selectivity, where we discussed the nuts and bolts of selectivity and the performance of switchgear or circuit breakers. My colleague Craig Abbott from Queensland will be answering questions fielded during this presentation. If you have a question, simply type it into the chat box and it will be looked after in due course, or we'll answer your questions as time permits after the presentation. Some of the subject matter in this webinar will be around real applications and how we use specific combinations of devices to achieve a result. We'll also look at the ideal in system design versus the economic reality of project delivery. So how do I achieve an appropriate selective system? What is a type A MCCB and what is a type B? What is zone selective interlocking? What are my design criteria and my actual priorities? And what's my realistic outcome? Firstly, let's cover the basic differences in circuit breaker selectivity types. This should help us to understand some of the selection issues at hand, the behaviours and differences with protection types. There's confusion occasionally about breaker selectivity and their classification types according to AS/NZS 60947 Part 2, being Type A and Type B classifications. Attached to the testing is a lot of provisional information that may and does muddy the waters as to what constitutes what type of breaker. I'll try to simplify the identification of those types and why. Classification exists and is broadly specified as follows. This is quite wordy, so please bear with me. The selectivity category A, these are circuit breakers not specifically intended for selectivity under short circuit conditions with respect to other short circuit protective devices in series on the load side, i.e. without an intentional time delay provided for selectivity under these short circuit conditions, and therefore without a short time withstand current rating according to clause 4.3.5.4. Now let's not complicate the issue with this clause and table 3, except in short to say that the clause defines the meaning of ICW or short time withstand current. Now short time withstand current is the rating of current multiplied by time that a device needs to endure before it becomes a current limiting device, as in it begins to open. Devices that have no natural mechanical operating action to short circuit current, such as isolators, load break switches, and air circuit breakers, are rated with STW or ICW of a particular fault current in KA for a particular number of seconds or part thereof. Category A circuit breakers react to short circuits immediately. Selectivity type B states that circuit breakers specifically intended for selectivity under short circuit conditions with respect to other short circuit protective devices in series on the load side, i.e. with an intentional short time delay which may be adjustable, provided for selectivity under short circuit conditions. Such circuit breakers have a short time withstand rating according to clause 4354. There are a number of riders on the behaviours and expectations of ratings along with the previous explanations. However, in a nutshell, the description is a fair indication of the behaviour of electronic OCR MCCBs, and while still highly current limiting in their operations, are frequently referred to and classified under the banner of Type B. This is because the command to unlatch the contact set is often delayed slightly due to processor speed and or programmed intentional delays. Air circuit breakers, generally speaking, are designed and manufactured to hold onto short circuit faults to allow devices downstream to operate and interrupt the faults. The overcurrent relays need to be commissioned and set to appropriate time current coordinate levels to ensure a proper coordinated protection system is in place. So let's now look at bringing all of the pieces and levels of selectivity together to understand at the end of the day what needs to happen to ensure we achieve the desired result. At this point, I'm assuming that our audience has viewed and understood Selectivity 1 and Selectivity 2, presented a little while ago and still available for repeat viewing on NHP's YouTube channel. As we've discussed, selectivity is not just one thing. Selectivity is a chosen level of behaviour of electrical protection devices in a circuit. The chosen level may be different for many applications and installations. From AS/NZS 3000-2018 compliance, where we understand our obligations and objectives for reliability of supply and coordination of protection devices for standard applications. Through to our obligations for safety, service, circuit and general supply selectivity, right through to enhanced selectivity to full prospective fault level of the installation. After compliance to the wiring standard, safety service selectivity, general supply selectivity where the stated ratios between untested devices is deemed adequate or manufacturer's data to be consulted, and the requirement of between 30% and 60% of arcing fault current, and again in the notes section, with a requirement to consult manufacturer's data and the need to use cascade information where appropriate. All of these details are covered in Selectivity 1 and Selectivity 2 presentations in detail. After meeting these obligations, the choice is an agreement between the designer engineer, the contractor installer, and the end user installation owner. The more critical or high risk the installation, theoretically the greater the level of selectivity and supply security that is required. The obligations from the wiring rules right through to full selectivity, top to bottom of the facility. We need to do one very important analysis, and this is an installation operational strategic risk analysis based on possible financial and data loss costs should there be an interruption to the supply. The interruption might mean anything from the loss of a distribution board feeder for 5 minutes to a full-blown main switchboard power loss for hours or possibly days. The delays could be caused by multiple devices tripping during one fault event and the difficulty caused trying to identify the origin circuit and root cause of the trip, right through to failure of the selected components to adequately protect the system, causing severe damage to conductors or pollution in switchboards. The higher the risk, the higher the fault level ensuring selectivity is warranted. The higher the risk, the greater need for monitoring of the system energy requirements, and depending on the type of installation, involving another subject relating to reliability of supply, is the use of appropriate backup power systems and reliable transfer switching devices. This brings us to another area of selectivity involving these devices and maintaining multi-levels of inbuilt reliability. On the subject of system monitoring, breaker history and a greater emphasis on breaker service life needs to be applied. This is especially important in the industrial sector, however it's also another subject for another day. Whichever way it goes, the greater the risk, the greater the investment required. There is a misunderstanding that by referring to manufacturers' selectivity and cascade tables, the chosen combinations of devices will automatically discriminate at all levels of fault. Now, this is not always the case. The devices in these tables are tested at these extremely high levels of fault to determine their safety and upper limits of performance. The instantaneous trip adjustment is normally set to worst case scenario and at the highest level to increase the pickup level to trigger a contact release. The tables contain no information on the ability to be adjusted and their expected behaviour under low levels of fault that involve overloads and very low levels of instantaneous fault. So we'll have a look at a theoretical application. Let's start at the top end. An example of what a medium-sized commercial building might have as a supply system. A 1250 kVA transformer, 11 kV to 400 volts. Supply capacity of the transformer of 1800 amps and a 6.5% impedance. The three-phase perspective at the transformer of 27.8 kA. At the main switchboard, we've reduced the perspective to 20 kA. We have a 1600 amp MCCB feeding a split bus, where an 800 amp thermal magnetic MCCB is the outgoing feeder to another switchboard downstream. So here's our application. In the black is the 11 kV fuse upstream of the transformer. The red curve is the 1600 amp electronic MCCB, and the blue curve is the 800 amp thermal magnetic MCCB. Even though our selectivity tables show us 20 Ka selectivity between the two devices, the 800 amp thermal magnetic cannot be adjusted far enough back to avoid a conflict in the time current area. Here is the same example showing the second breaker as an 800 amp electronic breaker. This will allow us the flexibility and adjustability to give us no conflict in the time current areas of the curve. Clearly, the cheapest option and most expedient choice doesn't give us the result we're looking for. In the downstream circuits, we show a 100 amp MCCB and a 50 amp miniature circuit breaker. At maximum setting of the MCCB, we have a time current conflict in the instantaneous section of the curve, even though our selectivity and cascade tables show us a 30-30 result. So with our structures and operations becoming more and more current dense, the need to reticulate multiple layers of distribution, often with similar or essentially the same settings on protection devices, how can we reduce the likelihood of many devices tripping in the event of a single fault, especially in the low to medium area of short circuits? Essential installations and services such as hospitals and water treatment plants spend multi-millions of dollars on state-of-the-art equipment and systems. However, unfortunately, on occasions, connect them to inadequate primary, secondary and tertiary supply systems and backup systems. And the backup systems often fail when they're needed. And on that note, coming soon, we'll have Transfer Switching Techniques #2 webinar available for viewing. Similarly, the opportunities to design and install a robust and predictable electrical supply and protection system often comes down to motivation and money. Now, that's just a fact of life, and unfortunately, an all too common cause of losses, sometimes snowballing to further issues requiring reticulation upgrade or total replacement. In the example shown earlier, breaker adjustment is just not possible even if we cheat and adopt a single line depiction and disregard setting, component and operational tolerances. One of the only ways we can overcome this is through a method called ZSI, or Zone Selective Interlocking. ZSI does not replace breaker behaviour owing to inherent trip characteristics and therefore does not technically contribute to wiring rules conformity. However, it does allow difficult high current density design issues and the need for selectivity to be overcome and a predictable outcome for continuity of supply. It is, however, primarily used to reduce let-through energy in the event of a low-level fault. Here is a for instance where a number of breakers are in series arrangement and their short time or STI settings are with similar values. In these instances, not only the issue of selectivity clashes can arise, but in current dense installations, the reduction of let-through energy upon a short circuit incident can be critical. The STI settings are generally based on a multiple of IN, or nominal current range, say between 2 times IN and 14 times IN as a low-level short circuit current pickup value. Each of the breakers has a time lag level threshold. Each breaker's countdown clock is armed upon crossing of the short-time short circuit current level threshold. The third breaker in the line has its STI current level set to an appropriate minimum time delay, say of around 50 milliseconds. The next breaker may be set above that, say between 100 and 500 milliseconds, and the top breaker, or breaker 1, set at least at 500 milliseconds. Upon initiation of a low-level short circuit, the current may rise through the current thresholds rapidly, and due to setting tolerance, differences in clearing rates of downstream breakers, multiple trips may occur. For these applications, the use of a ZSI system or Zone Selective Interlocking system may be enough to solve the conflict. The Zone Selective Interlock acknowledges where the fault is downstream of the nearest breaker feeding it. The breakers use a high-speed digital signal to lock out the other breakers upstream and allow the immediate feeder to interrupt. In this sequence, a fault of a theoretical level of XKA above the short-time instantaneous threshold of both breakers occurs below breaker Q2. Breaker Q1, set at 500 milliseconds delay, sees the fault and the OCR checks to see if input ZS1 has received a signal from breaker Q2. If it has, the OCR is armed and starts its delay clock ready to interrupt. Breaker Q2 sees the fault and the OCR checks input ZS1 to see if a signal has been received from breaker Q3. In this case, it hasn't, so the OCR bypasses its delay setting of 400 milliseconds and interrupts the fault instantly. If the breaker Q2 has a failure such as a welded contacts or something of that nature and can't interrupt the fault, Q1 will time out and interrupt the fault in 500 milliseconds. A sophisticated and successful high-value installation may employ a number of selectivity techniques, including zone selective interlocking to increase the robustness of the system under fault conditions and limit let-through energy into the system. So what are my realistic outcomes? Full selectivity is not essential in all applications and often not easily achievable in some designs unless compromises are made. The dynamics of short circuits, high-level faults particularly, may dictate an escalation of frame sizes or addition of ACBs in the system if full selectivity is needed. This, along with other techniques such as addition of magnetic-only breakers in some parts of the system or the use of zone selective interlock to improve system predictability. The risk factor should have some bearing on the level of selectivity chosen. However, understand risk and investment in the outcome both equate to the possibility of outgoing dollars. And don't forget the reliability and the design of the backup system, and this needs to be incorporated into the selectivity design to ensure proper operation in the event of a short circuit fault. So, in a nutshell, as discussed earlier, the most robust discussions we need to have are cost versus loss, weighing up the risk and possible liabilities. A robust, reliable system may need to apply many techniques to ensure a predictable result, given all possible scenarios. Understand the actual operation and performance of the protection devices and therefore the expected performance of the system as a whole. Apply the appropriate measures for the application. What I've just presented is the ideal. You need to understand what rung of the ladder is appropriate, and is the upfront additional expense worth the value it brings should the solid excrement contact the rotating ventilation device. If you follow the link below, it'll take you to our website location for more technical recorded webinars. We trust you enjoyed today's contribution, and thank you for tuning in. I'll be available for a short time now to take any questions entered in the webinar chat box. If we don't get time to get to yours, we'll answer directly via your email. Alternatively, feel free to email me directly with your questions, and look out for our webinar on selectivity number 4, coming soon. There you go.
Well, thanks for that, Steve. A very informative webinar on selectivity that works on the back of Selectivity 1 and 2 that we've previously published. Very informative. And Steve, I believe you'll be on the line for the next 10 or 15 minutes. If any attendees would like to pose any questions, we can certainly answer.
Thanks, Craig. Yeah, we'll be hanging around for a little while here just to see if anybody has any questions on the webinar. But as you said, yeah, we've done a couple of these webinars before, and they are on our NHP YouTube channel. If you want to tune into that, get onto that one. And there's
along with many other webinars, Steve. Along with many other webinars of many electrical engineering disciplines, from Type 2 coordination through to condition monitoring. Very informative, simply from channel NHP on YouTube, or you can go to the NHP website. Also, like all attendees, if you could please fill out the survey at the end of this presentation. And Steve's...
We've got a question up now, Craig, actually, from Len Vella. Len has asked, is ZSI delay time adjustable? Now, the ZSI function, Zone Selective Interlocking, actually is an instantaneous operating trip signal for the breaker that is identified as immediately upstream of the short circuit or the issue, and it locks out the other breakers, or it bypasses its own time delay for the short time delay instantaneous section of its curve. So in other words, if you've got 2, 3, 4, 500 millisecond time delay in the instantaneous area, at let's say it's around about 10 times its or 8 to 10 times its nominal number, so you know, a couple of thousand amps, then it will bypass that time delay and will immediately open. And that's the point of the Zone Selective Interlocking function. It's to take all of the time delay out of the issue so that the resultant let-through energy doesn't go through the system and potentially damage the electrical system downstream. I hope that's answered your question, Len.
Thanks for that, Steve.
Well, it seems we don't have any more questions coming there, Craig. So what we might do is, as Craig said, I'll stay on the line here. If you'd like to type your questions into the chat box, and I'll stick around and answer them for a little while. But I think it's probably just about time to probably go off air now. We're just about out.
We have another question coming from Daniel at Cardno. If I can just pose that question to you, Steve. How does the MCCB type selection tie impact into the surge protection device?
Surge protection device. I'm not sure I understand what that question is, Daniel, because MCCB type selection, I can only think of that as being a type A or a type B. And surge protection devices, well, circuit breakers are only basically used in front of surge protection devices to protect against short circuits within the surge protection device when they come to end of life. So I'm not sure what that question means.
I guess if I could put a take on that, yes, the MCCB or MCB more likely for surge protection devices is there for protection and isolation. But at the same time, there are no requirements for that circuit breaker to fulfill selectivity. So if we're looking at an installation, and let's suggest that we have a 63 amp circuit breaker in a distribution board being the largest breaker, it's for surge protection, then maybe our next breaker might be a 50. It's the 50 we use in our selectivity because you don't require selectivity for the surge protection device. So I hope that answers the question, Daniel.
Here's one from David Morgan. He asks, where you have multiple downstream breakers, how are the different signals sorted out? Well, thanks for the question, David. The signals, when you're talking about zone selective interlocking, I assume, the signals are just basically a digital signal. So you have an input signal, so you've got ZSI1 and ZSI2, and when devices receive a signal from the downstream breakers, it then says that the short circuit is downstream of that particular breaker. So that ZSI2 input, if it gets a signal on that, it says, okay, some other device downstream is looking after this short circuit, and I'm just going to go about my normal time delay and count down on my normal time delay. The device that hasn't got a ZSI2 signal, I think it's a ZSI2 signal, will bypass its normal countdown timer and instantaneously open. And that goes to a question we also have here from Len Vella, a secondary question from Len. He said, if the downstream breaker contacts are welded closed or fail to open, how does the upstream breaker know when it's okay to trip if they're connected by ZSI? Well, the ZSI doesn't do anything except tell the other breakers to go on with their time delay should that low-level short circuit cross over its short time instantaneous point. So they will just continue their countdown, and if the downstream breaker doesn't open due to welded contacts or some other issue, then the upstream breaker will go about its normal opening procedure and just allow the let-through energy to go through.
It seems like we've had a plethora of zone interlocking questions. Just moving away briefly, we've got a question from Bradley at Worley. Often find that when swapping to a backup supply, i.e. UPS, the downstream breakers will not operate before the UPS would trip in the event of a short circuit or a downstream circuit. Any products that could isolate a circuit fault before UPS trips?
Well, that's a good question. Generally speaking, Bradley, the UPS is going to have its own cutout activation when it detects a short circuit downstream. When you're talking about UPSs, often the short circuit through the back end of the UPS is very, very low. Having said that, when you are configuring UPSs in a system, you often have a UPS bypass system in place. So you're going to have a device downstream of the UPS which will reflect the bypassed short circuit possibility or the bypassed prospective fault current downstream of the UPS. When the UPS is feeding it, the prospective short circuit is way, way lower than it would normally be when it's bypassed. So sometimes you're going to have a mismatch or an issue with the downstream circuit breakers as far as the amount of energy that it takes for them to trip. And often the UPS will trip way before that amount of energy can go through that circuit breaker. So the UPS will open up its own outputs so that it bypasses that the need for a circuit breaker trip. That's the best way I can actually answer that one.
Thanks for that answer, Steve. In respect of any questions, if you have further requirements on any questions that are asked, you can pose these to Steve at syoung@nhp.com.au, and then, of course, we will be able to provide much further information. Back to ZSI, Steve. Mayank from WSP. Can ZSI be implemented between multiple switchboards, i.e. main switchboard and DB?
That's a good question. I would have to go back and check on what the length of run limitations are. But generally speaking, the ZSI is a pluggable function or a cabling function by twisted pair. So that's a good question, and I will have to answer that one on the back end, I'm afraid, so I can do a little bit of research into the maximum lengths. The short answer is yes, it can, but it is going to have some limitations. My guess is on the length of run of the cable due to the signal, the digital signal.
Absolutely, and it's simply a twisted pair between breakers, so akin
Correct.
to typical Modbus RTU type installation of a twisted pair daisy chain between devices. I believe up to 12 ACBs can be zone interlocked.
Actually, 14
at the same time. 14.
We can actually get 14. You can interlock with the system. You can interlock up to 14 ACBs and a selection of moulded case and ACBs if you really want to do it that way. But the zone selective interlock signal is only a digital signal. It's not communications. It is just an on or off signal.
And we'll get back to Mayank with that one. Back. So we've got David Morgan from the Uni of New South Wales. So all breakers in a particular zone are daisy chained or on a bus which feeds to the upstream breaker. So the zone interlocking yet again.
Yeah, David. Look, in theory, you can use this technique in any series circuit. So you can use them. You can have 10 on a bus, all interlinked to a breaker that feeds that bus, if you wish, or you can have 14 breakers in a row in a series circuit. So it's entirely up to you the way that you utilise this, and don't forget that this system it's not specifically for selectivity. What the system is meant to do, what its main purpose is to reduce the amount of let-through energy into the downstream circuits on a short circuit by bypassing the time delay, which is on the short time setting of the circuit breaker. So, yes, you can put any breakers on that system you want, but you need to understand the actual reason that you are doing it.
Just in brief consultation there, Steve, with our product team, as this is a live webinar, I'm just discussing with one of our commercial engineers. When we look at 14 ACBs locked together in zone interlocking, we can there make some assumptions that we can have reasonable lengths of cables, because it's not often we're going to see 14 ACBs within the same 10-metre space, shall we say. So because of the actual length of the wire, we're now getting data from Terasaki, but at this stage we haven't got that to document. So very good question, and at the same time we will be able to provide that via email once we get it from the product manufacturer.
Well, again, Craig, I agree. And the thing is that if you have very long lengths of wire, you need to be careful of the input and the output of the digital signal, the impedance of the receptor, and the impedance of the actual wire, to ensure that the signal that comes from the downstream breaker, or whichever breaker, is going to have enough ergs. Let's use a technical term and call it ergs to activate the zone selective interlock signal in the upstream device. So we can get back to the maximum.
Yeah, and looking at segregation, but obviously with it being a digital signal as opposed to mains, we're looking at how you'd run it at the same time. So we'll certainly come up with that data for a very good question. I thank all the attendees. Questions are now complete. And look forward to your attendance to future NHP webinars, and please don't forget the survey. Thanks very much,
Greg.
Steve.
Thanks, everybody. Catch you later. Bye-bye.